Hello again, Physics 30s. In today's lesson, we are going to talk about another very important experiment or observation dealing with something called the photoelectric effect. And in order to explain the photoelectric effect, we're going to have to use our new model of light, that being the wave-particle model of light. Maybe just before I get going, let's just summarize what we know about this. Okay, so let's look at the different models of light. So we have the particle model. So in your particle model, if you have a light source, you're just firing a bunch of little light bullets in every possible direction. Again, the key thing about looking at a particle is a particle is discrete. So again, there's separation between these different light bullets. Then we have the wave model. There's a couple of variations of this, which tells us that if we're looking at Huygens and Young, that light is a transverse wave that just radiates outward in every direction from a source. Or if we look at James Clerk Maxwell, he would have said that it is an electromagnetic wave that's radiating outwards from the source. And again, an electromagnetic wave has oscillating electric and magnetic fields that are perpendicular to the direction the wave is moving. And then from last time, we have Max Planck. Who comes up with the wave-particle model. And we'll call that wave-particle model a photon. And the way that one works is we have elements of both of these models. So what we'll be doing is we'll be firing little bullets in every single direction. So little bullets in terms of discrete units. But if we were to zoom in on one of these little discrete bullets, one of these little photons, these photons would have a wavelength, which means that in the right situation, you can get the photon to diffract. You can get it to interfere with another photon. Or if you put it through certain filters, you could polarize it, which is going to decrease the intensity of light because you're reducing which plane it can actually vibrate in. So we're going to look at this wave-particle model, the photon model, and start applying it to different experiments that physicists were unable to explain. Learning outcomes are to 1, describe the photoelectric effect in terms of the intensity and wavelength or frequency of the incident light and surface material. 2, describe quantitatively photoelectric emission using concepts related to the conservation of energy. And then 3, describe the photoelectric effect as a phenomenon that supports a notion of the wave-particle duality of EMR. Okay, so let's look at the photoelectric effect. When you see this word photo, the word photo does make reference to light. So in the photoelectric effect, what we're going to do is we're going to take light energy and we're going to convert that into electricity. This is going to be like a bit of an explanation in terms of the operation of like how solar panels work, or if you have like one of those old calculators that has like solar panels built into it, which can function if you're in a room that has bright light in it, and then it can actually power the calculator. However, we're going to start with our favorite apparatus, with that being a cathode ray tube, although there's a little bit of an adjustment here compared to the ones we looked at in previous lessons. So in this cathode ray, I just want to point out, first of all, there is no power source. So in every other cathode ray tube that we looked at, we had like a jumbo battery probably located in this area. And this jumbo battery basically did work to move electrons, and the electrons could jump from the cathode to the anode. Enough power in that battery to make them jump across the gap. So we do not have a power source here. Our only power source is light. So what we do is we shine light at the cathode. And when I shine light at the cathode, it can actually take some of these electrons and it can make them go across the gap. And then basically just complete the circuit. The A with the circle is an ammeter. An ammeter would just detect the presence of electrical current I. So that's the only point of having that. So when high frequency light, and we'll talk more about the significance of being high frequency light momentarily, is shone on a metal cathode in a cathode ray tube, cathode rays will be emitted to the anode even if you don't have a voltage source. So once again, the only thing that I have for input energy is going to be light from some kind of external source. This effect was actually observed by Heinrich Hertz in 1887. So this is a couple of decades before Max Planck came out with his wacky hypothesis about light being both a wave and a particle. So Heinrich Hertz, and I believe this is the same Hertz that we talked about in the lesson with James Clerk Maxwell's principle of EMR, where he performed that experiment with the conductors that had the gap and we were observing the sparks jumping across them. Okay, so Hertz. Observations related to this apparatus. The photoelectric effect only occurs if the instant light has a frequency above a certain threshold frequency. Okay, so what this means is not all kinds of light can do this. So let's look at two different photons of light. And the way I'm going to draw a photon is I'm going to draw like a little bullet, and I'm just going to put a wavelength inside. So we'll say we have a red photon, and we have a violet one. Now, which of these photons has greater energy? Well, the way that I usually always remember it is that red light is around 700 nanometers. So that has a higher wavelength. And then violet light has a lower wavelength, around 400 nanometers. According to our universal wave equation, where we have V is equal to F times lambda. And if we manipulate for the frequency, we'd have frequency is V over lambda, which tells me that F is inversely proportional to the wavelength, which means that if my wavelength is high, then the frequency is small. Or if the wavelength is small, the frequency is going to be higher. In terms of calculating the photon energy, well, use Planck's equation. E is equal to H times F, which means that if the frequency is high, then so is the energy, because there's a direct relationship between the two of them. Or you could have actually just gone directly from wavelength to energy, because there's also a part of that equation that tells you that E is equal to hc over the wavelength, which means that if the wavelength is big, then the energy is small. Okay, so my violet photon has more energy than the red one. So it could be possible that I shine like a red photon at this cathode and then nothing happens. It's possible. Why does nothing happen? Because you haven't reached the threshold frequency. The threshold frequency is the minimum frequency you would need for the photoelectric effect to occur. So if we shine a higher energy frequency photon here, then we could get the effect observed. Maybe. Depends on a lot of things. Okay, but the important thing is that this will only happen if your frequency is either greater than or equal to a threshold frequency. It's the minimum frequency that you need to meet for the photoelectric effect to occur. 2, different metals have different threshold frequencies. So if you had like one metal conductor that was aluminum compared to copper, the minimum amount of light required to make the photoelectric effect occur would not be the same. In fact, you're going to do a lab activity tomorrow or in the next lesson where you do need to determine the different threshold frequencies for different metal cathodes. We have an online app we can use to do it. 3, the effect is instantaneous, which means that as soon as you shine the light, the current should, it's like the effect should happen right away. Like you don't need to shine the light and then the energy doesn't need to get stored and then later on it happens. It's either going to happen right away or it's not going to happen at all. 4, if we increase the frequency of the light, then this is going to increase the speed and the kinetic energy of the photoelectrons. When I say the photoelectrons, it just means the electrons that are involved in the photoelectric effect. It doesn't mean that the electrons are suddenly turned into light. So just the speed of your electrons goes up if you increase the frequency. This shouldn't be surprising because according to Planck's equation, if you increase the frequency, then you increase the amount of light energy you're putting in. If I put more light energy in, I would expect to get more output. So the output would be more kinetic energy of these photoelectrons. Oddly enough, though, and we'll talk about this at the end of the lesson, if you increase the speed of the photoelectrons, this does not increase the current. This is weird because you would think, okay, if current is the amount of charge that passes through a point in 1 second, and if I increase the speed of the electrons, so if the increase of speed, they're covering more, or they're covering a certain distance in less time, then how could that not make the current larger? So we'll address that later on. This is something that Hertz could not properly explain. 5, if you increase the intensity of light, and again, the way we want to think about intensity now is number of photons. So for example, if you just shone 1 photon, and then you change that to shining 2 photons, you'd be doubling the intensity. Okay, so the intensity depends on the number of photons it's going to shine, and the more photons you shine, the brighter the light is going to appear. So if we increase the intensity or brightness of the light, then this does increase my current, the number of charges it passes through in 1 second, but it does not increase the speed. Again, this seems to be like a really odd thing, because you would think that the current and the speed are directly related. So Hertz was not able at this time to explain, I believe, observations 4 and 5. So he made the observations, but they kind of just had to sit on it. And I mentioned in the last lesson that at this point, physicists were getting pretty confident that they could explain most of everything. And there were just a few things they could not explain. So one of them was, why does the black body radiation curve die in the UV portion? We haven't answered that yet, but again, Planck came up with kind of like a cheat solution to get around it. Again, we'll address that at the end of the unit. And another thing they could not explain is observations 4 and 5, specifically number 5. If you increase the intensity of light, why does it increase the current but not the speed of the electrons? So it turns out that in order to explain these observations, we need to use the photon model. And as I'm sure, I suspect the way you reacted to the photon model when I told you that light is both a wave and a particle is you're like, this is ridiculous. Like, how can it possibly be both things? And I suspect that was the reaction from a lot of scientists back when Max Planck initially suggested the photon model of light. So it's kind of hard to gain traction with that model. However, there was a scientist who really, really liked the wave particle model of light. His name was Albert Einstein. Okay, so this is, I think Planck's quantum hypothesis is around 1900. So Einstein in 1905 is going to come around and start to explain these remaining observations of the photoelectric effect. Okay, so he's going to provide the following explanations for the photoelectric effect using Max Planck's photon model of light. Again, the photon model being the wave particle model of light. So here's how he explains the photoelectric effect. Einstein says that the electrons on the surface of a cathode are held there with a certain amount of binding energy. Why are they held there? Well, if you have like this is my cathode, okay, and you have electrons on the cathode, Well, the cathode itself would also have a nucleus, be made up of some protons. So there's going to be some electrostatic force that's going to hold the electrons to the actual cathode, an attractive force that holds them there. So they're bound there with a certain amount of binding energy. If you want those electrons to leave the cathode and get free of that binding energy, then you need to overcome it. So something has to be done to overcome that binding energy that's holding them in place. If you need to transfer energy into an object, that is the definition of work. Work is the transfer of energy into or out of an object as a result of, like, back in physics 20, we would have defined it as a result of a force acting over a displacement. We're not going to worry so much with the force and displacement part here as much as just identifying that if you need to transfer energy to something, you're going to do work. So Einstein called this amount of energy that a photon, so again, you're shining light at the cathode, so that's going to be my input energy. So you call that amount of energy that the photon must have to free an electron from the metal the work function. Okay, it should make sense. You need to do work to actually release the electron from the cathode. To calculate the work function, this is an equation you're going to find in the formula sheet. The work function is equal to Planck's constant times FO. And again, FO is the threshold frequency. So this equation has a direct relationship between the work function and the threshold frequency, which means that if a particular metal has a larger threshold frequency, and again, it would just depend on the nature of the material in terms of which metals have larger threshold frequencies, then if there's a larger threshold frequency, you're going to need to do more work to free the electrons from the surface. And again, we can calculate that by going H times FO. And just be careful, depending on what kind of units you want the work function to be in, you'd have to make an appropriate selection for Planck's constant, whether you want it to be in electron volts times seconds or joules times seconds. Observation 2. Since each individual photon, and again, we're going to assume our photons now have a frequency above the threshold frequency. Since each individual photon frees exactly one electron, increasing the number of instant photons striking the cathode will increase the number of electrons bumped off the metal surface. Okay, here's where you have to use the photon model of light to explain why you're going to have a larger current. Okay, so let's say that I just fired a single photon of light at this surface. We'll say the metal cathode is just made up of 3 electrons. This is a drastic oversimplification. So here's my photon of light, and I'm shining it. One photon of light can free 1 electron. So if this photon has enough energy, it's above the threshold frequency, it can free this electron, and then this electron would go across the cathode ray tube and then through the ammeter. And again, the ammeter, you could just think of it like this. We're measuring current, and current would be just counting how much charge passes through a point in 1 second. Okay, so if I had 1 photon and it released 1 electron, I would count 1 electron passes through there in a certain amount of time. Well, let's say now that I increase the intensity. So if I increase the intensity, I shine more photons. So if you shine a second photon, that second photon will release a second electron. And if that second electron then goes across a cathode ray tube, when I'm measuring the current here, well, I now have more electrons passing through a point in 1 second. And if I further increase the intensity, so again, if you increase the intensity, increase the number of photons, so I can increase it to 3 photons now, then this photon can release this electron. This electron jumps across the tube, and then in comparison to the just release having 1 photon, I now have 3 times the current. So this is the thing, like, you have to view light as a discrete unit to explain this, because what I have here is like 3 photons release 3 electrons. If you went back to the other wave model of light, it would just be telling you you're shining like a big electromagnetic wave at here, just 1 electromagnetic wave, but that doesn't really tell you how many electrons you're going to release, because you're not viewing the wave as discrete units. So it's very important that you view the light as little light bullets, because each of those light bullets can release exactly 1 electron. The more electrons you release, then the more electrons pass through a point in 1 second, and your current goes up. Okay, so again, just to emphasize that point, there is like this perfect relationship between the number of photons you shine and the number of electrons that are going to be released. Again, that's where we need to use the photon model of light to explain this. And this is where Heinrich Hertz would have been unable to properly explain that one observation. I think the other one is that if we increase the intensity of light, then this has no effect on the, let's go back here for a second. Yeah, if we increase the intensity of light, it's the number of photons, that increases the photocurrent. Photocurrent just means the current of the electrons, but it doesn't increase the speed. Because all these photons are doing is they're just releasing the electrons, in which case it doesn't matter. Like if I shine one photon and release an electron, or I shine two photons and release an electron, the electrons are going to be released at the same speed. Increasing the number of photons doesn't give them each electron more energy because only one photon is striking one electron. So they all get released at the same speed if you're looking at light at a constant frequency, monochromatic light. The other observation tells us that if we shine a photon and it has more than the minimum energy required to cause the photoelectric effect, any excess energy will be given to the electron in the form of kinetic energy. Okay, so let's just focus on the cathode. So what's going on here is let's just focus on one single photon. So we have one photon of light that comes in. This photon of light has an energy of h times f. This photon of light is going to strike this electron on the surface. And what it does is when this photon comes in, it can only release the electron if it has enough energy that's bigger than the work function. After it's overcome the work function, whatever energy is left over, that's what the ejected electron is going to get. We can actually view this from a conservation of energy equation. So let's break this down. Conservation of energy, so we'll view it in the terms of like the input energy is equal to the output energy. So what's my input energy in the photoelectric effect? Well, whatever energy the photons are carrying. In this case right here, we're just carrying a single photon, so my input energy would just be h times f. The output energy, well, you have to do two things. You first will have to overcome the work function. You have to do work to free the electron from the surface, and then whatever's left over goes to the electron as kinetic energy. Therefore, we'd have the E photon would be equal to W plus EK of the electron. We could expand this one step further. The energy of a photon is h times the frequency, and that would be equal to the work function W plus 1/2 mv squared. So the 1/2 mv squared term is everything related to the electron that's being ejected. So that'd be the mass of an electron in that equation. So I believe the other observation told us that if you increase the frequency, you increase the kinetic energy. Well, we can see this directly in the equation here. So in this equation, I believe there's a partial relationship between the frequency and this term here. This term right here would be the kinetic energy. So this tells you, because the work function for a metal is constant, so if you increase the frequency, then you're putting in more energy. If you're putting in more energy and you have a constant work function for a metal, that means that the electron gets more kinetic energy. So conservation of energy can nice and easily explain how this one works. And most of our problems are going to involve utilizing this physics principle and just playing around with this expanded equation. I should point out, though, that the equation is not on the formula sheet, that boxed one. Therefore, it's one that you need to understand how to derive. It's not hard to derive the equation as long as you understand the photoelectric effect from an energy perspective. Then deriving the equation is easy, and then it'll just be a little bit of work to kind of play around with the equation. I did want to warn you about one thing, though. When you do use the above equation, make sure that both the units for H and the work function are in joules times seconds and joules respectively. And here's why. When you calculate kinetic energy, typically you have mass in kilograms, and then you have speed in meters per second squared. Oh, meters per second all squared. Let's erase that. I was thinking of the units for acceleration. Okay, so let's go back to this. Meters per second all squared. That gives me kilograms times meters squared per second squared. A kilogram times a meter squared per second squared is a joule. It is not an electron volt, which means that when you're playing around with this equation, you need to make sure the work function is in joules. Therefore, if a problem gives it to you in electron volts, you need to convert it. And also with this here, there's two different values for Planck's constant. So the one you'd want to use would be the one that's in joules times seconds. That's 6.63 times 10 to the negative 34 joules times seconds. If you use the other one in terms of electron volts, 4.14 times 10 to the negative 15 EV times seconds, and it's not going to work out. So just a word of caution when you are solving the problems in terms of the units. Okay, now one other thing. This is like that one contradiction. So if increasing the frequency of incoming photon increases your speed, how can it possibly not increase your photocurrent? Okay, I'll use a little illustration to try to, as best as I can, explain this. Again, this seems very counterintuitive because if you increase the speed of the electrons, so again, if we focused on all these electrons here, and if I increased how fast they were moving, and if I'm sitting here, and this is my goal in life, is just to sit here and just stare at this and this vertical line and count how many electrons pass through there in 1 second. If they're moving faster, how could I not be counting more passing through in 1 second? Okay, again, it seems very, very counterintuitive. Well, here's why. Okay, so let's say that you shone a single photon of light, and I'm gonna pick let's do green in color. I'll pick a lower frequency photon. So I shine just a single photon of light at this end of the cathode ray tube. So if I'm above the threshold frequency, what this would do is this would then fly across the tube, and you're gonna get this like domino effect, where like, I don't want to call it domino effect, but you're gonna get this effect where like kind of like everyone just shifts forward in line by one. You can think of it like as a big line waiting to like, I don't know, get some food from the concession at like an overpriced Calgary Flames hockey game. So this guy comes across, then all these guys are gonna, basically every one of these gets bumped forward by one. So like this one will move over here, he moves here, this one moves there, this one moves there, this one moves there, here, here, here. And then if I'm counting the number of electrons that jumped across that gap, it would just be one electron. One electron jumps across the gap here, okay? Now, if I increase this to a higher frequency photon, so let's say now that I turn this into a purple one, it's the purple photon now, and I shine it at this electron. Okay, what would happen? Well, this guy would go faster across the tube. There's no question about that because it has higher kinetic energy. But let's see what happens in terms of the line shifting. So in terms of the line shifting, once this guy comes over, it would repel electrons, so they'd all just once again hop forward one position in line. The only difference is that when we change our position in line, we just do it faster. So like, what's the order? Like, let's say like you're in the cafeteria and you're like waiting in this endless line to get food. So let's say that like right here, this is where the cash register is. So this would be like person 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is 15th in line. This is 16th in line. If I only have one cash register open, okay, what would happen is like once they serve this person and they go away, then everyone shifts forward in line by one. Increasing the frequency would, because I only have one register open, would make everyone shift forward in line by one. But with the increased frequency, they just do it quicker. So like the person might say next or something, and we'd all shift forward to our next position in line, but we just do it quicker. That doesn't make more electrons jump across this gap, though. Okay, so with a higher frequency, like this electron would go from 16 to 15 quicker, but I still just have one electron doing it. Now, this would be different if I then shone a second photon here. If I shine a second photon, it'd be like opening up a second cache register. So then like I'd launch another electron across there. So this time around now, 2 electrons are going to jump forward in line. So this one would go to, this is getting pretty messy, so let's go to a different color. Oops. So this one would then jump 1, 2 spots over, and then this one would go 1, 2 spots over. So by shining more photons or increasing the intensity, I increase the current. But if you keep the number of photons the same, the intensity the same, yeah, the electrons shift spots and line faster, but that doesn't change how many of them pass through a point in 1 second. That can only be affected by what the actual intensity or the number of photons you shine. I hope that analogy to a cache register and like how many are open made a little bit of sense. Okay, so that's it for this lesson, the photoelectric effect, and you can complete the assignment called the photoelectric effect. And then in the next lesson, there is going to be a lab that I'm going to call mandatory that's going to use an online app that does a bit more of an extension with the photoelectric effect and approaches it more from a graphical perspective and also introduces a new equation into it. And I will talk to you lecture-wise in the lesson after that lab. We're going to get into discussion of X-rays and the Compton effect. And I'll talk to you